The motivating question for me today is, can we ensure the safety of the $100 billion or more of crypto assets that are currently deposited in decentralized finance or DeFi platforms? The examples of DeFi platforms that I have in mind are especially decentralized exchanges, which function as the DeFi counterpart of a stock exchange, or a lending protocol, which function as a DeFi counterpart of a bank with borrowing and lending capabilities. When I say the safety, I mean in the sense of ruling out economic or financial exploits as opposed to purely technological or OPSEC type of vulnerabilities. So in other words, the type of vulnerabilities that I want to think about are what we can call arbitrage. And so we're interested in whether the absence of arbitrage can be guaranteed. So in a typical decentralized exchange or DEX, there's a liquidity pool which holds pairs of assets against which traders may transact by choosing from among the trades that are offered by the DEX. And that DEX algorithmically determines what output bundle to offer in exchange for each proposed input bundle. So, for example, a pool may hold some quantity of a blue coin and a red coin. Trader can come to the pool and pay the blue coin and receive the red coin, or can pay the red coin and receive the blue coin. Now, who funded that pool? That would be the liquidity providers, who can add both coins to that pool in the same ratio as the current composition of the pool, and thereby receive shares, LP shares, or liquidity provider shares, representing fractional ownership of both assets in the pool. So if you go to the leading decentralized exchange, Uniswap, and you pull up one of the pairs that they have available to trade, this would be the Ethereum versus USDC, USDC being a stable coin that tracks $1 US. You can type a 5 into the interface, and it will say, okay, if you send it 5 ETH into the pool, it'll send back 17,700 USDC. Or you can type 10,000 into the interface, and the pool will return back to you 2.81 ETH if you submit 10,000 USDC. But then there's also the interface for a liquidity provider. The liquidity provider is allowed to add both coins to the pool in the same proportion that they currently exist in the pool, and for that they will receive some fraction of ownership of the coin pair in that pool, and collect some amount of the fees from the traders who transact against the pool. So if X1 and X2 are the quantities of the blue coin and the red coin in the pool, what the pool does is to maintain a constant product of the quantities of X1 times X2. If you calculate the instantaneous rate of change of X2 with respect to X1, you find that turns out to be X2 divided by X1. So in other words, the implied price of the blue coin in units of the red coin is the amount of the red coin in the pool divided by the amount of the blue coin in the pool, X2 over X1. So traders can interact with the pool, but you're always maintaining that constant product. In this case, the constant product is 3,600. So whatever trades the traders do against that pool, after each transaction, the 3,600 product is maintained. Now, no matter what transactions happen, it's never the case that you start out with some amount of blue coin and red coin, and you end up with an amount of blue coin and red coin that is unambiguously worse than what you started with. In other words, it's never the case that you end up with less blue coin and less red coin, at least one of them being strictly less. So in that sense, this mechanism is arbitrage free. Okay. But then what about the liquidity providers? Well, a liquidity provider can come in and, let's say, double the liquidity in the pool. Well, if they double the liquidity in the pool, then both the red coin and the blue coin get multiplied by 2. Then if you start out with 60 liquidity shares, then another 60 get minted and distributed out to the liquidity provider who provided that extra liquidity. And so now that liquidity provider owns half of the liquidity shares. They own 50% of that pool now. If a trader then comes along and decides they want to buy 48 blue coins from the pool, then the blue balance in the pool will go down by 48, but the red balance in the pool will go up by the amount collected from that trader in such a way as to maintain the new constant product. The new constant product is 14,400, and that new constant product will be maintained. If now the liquidity provider wants to remove 80% of the liquidity from the pool, then everything gets cut down to 20% of what it was. If that liquidity provider can redeem 96 liquidity shares in order to claim that 80% of the pool. Okay, so in what sense is that arbitrage free once you allow liquidity providers to make these deposits and withdrawals into that pool? So that's one of the questions that we want to think about. Okay, but now suppose that there are 2 pools on the same assets. So it's still just the red asset and the blue asset, but now there's not only Uniswap, but some other DEX. Pancake Swap is also offering a pool with those same 2 assets. So the X1 and X2 are the balances of the red asset and the blue asset in the Uniswap pool, but X3 and X4 are the balances of those same 2 assets in the Pancake Swap pool. So, okay, well, neither of those 2 pools admits arbitrage individually in the sense that they're all, when you look at each pool by itself, disregarding what's happening in the other pool, it's still going to be the case that you never have a bundle being reduced to a dominated bundle in the sense of both quantities being smaller and one of those 2 quantities being strictly smaller. However, if you think about the aggregate holdings of the 2 pools, then in aggregate, there can be an unambiguously disadvantageous transformation to the pool. Because if you start with 8 blue coins and 2 red coins in the first pool, and 1 red coin and 9 red coins in the second, then there's a transaction that can maintain the 16 by going to 4 and 4. There's another transaction that can maintain the 1 and 9 by going to 3 blue coins and 3 red coins. So what's happened to the aggregate holdings is that the 8 plus 1 blue coins and the 2 plus 9 red coins, which were 9 and 11, have gotten reduced to 7 blue coins and 7 red coins. And now that system of 2 pools has, in some sense, become unambiguously worse. And if we define arbitrage in that sense, then arbitrage does exist. And if you regard that as a vulnerability of this system, then this system is subject to that vulnerability.
This is because the pools have different prices.
Yes, it's because the pools have different implied prices. Because in the first pool, the price of the blue coin is one fourth of a red coin, and that's by the formula here, right? The the price of the blue coin in units of the red coin is the amount of the red coin divided by the amount of the blue coin. And the price of the blue coin in the first pool is 0.25. The price of the blue coin in the second pool is 9. So there's a large discrepancy between the implied price of the blue coin in the first pool and the implied price of the blue coin in the second pool. And in some sense, that's the origin of the arbitrageability of this system of two pools. Okay, so that's kind of the motivation, right? So this is kind of setting the stage for this idea that we want to be very flexible about what's meant by arbitrage. In some cases, we want to define arbitrage by this kind of relationship where it's just that the amount of this case where you have a transaction that strictly reduces either the blue or the red quantity without increasing either of the quantities. And in other cases, we might have a different definition of arbitrage where we look at the sum of the blue coins in two different pools and the sum of the red coins in two different pools. And it could be that arbitrage exists in some sense, but not in some other sense. And so we want to be very flexible about what that means. We also want to be very flexible about what kind of system we have, whether it's a single pool, whether it's a system of multiple pools, whether it's not even a DEX, whether it's some type of lender that can be expressed in terms of transitions of state variables. Yeah.
So meaning basically this, so far we are saying that if we only look at one pool, then there is no arbitrage. If we look at two pools, then there could be an arbitrage. And this arbitrage is basically a collective arbitrage, in the sense that it's not the liquidity provider himself. Individually with the provider is being arbitrage, but the collective of all liquidity providers from both pools.
Right. It's the liquidity providers in aggregate, which we're agnostic about whether that's different people or different wallets, or whether it could be one person who has shares of both pools, and therefore when, if I have a 10% share of each pool as a liquidity provider, then arbing the collective aggregate of the two pools ends up arbing me because I own 10% of each pool. So it's arbitrage from the standpoint of the liquidity provider. At least that's the way that these two notions of arbitrage have been defined. Okay. So if a pool now holds quantities x1 and x2 of the two coins, then we can kind of formalize the operations of Uniswap v2 by saying that a swap can transform from one state to another, provided that the product remains the same. And liquidity can be added or subtracted by taking the pool quantities and multiplying by a scalar that is greater than 1 to add liquidity or less than 1 to remove liquidity. But really a more precise description would be to add another state variable, XL, which will denote how many LP shares exist, how many of those liquidity shares are outstanding. A swap doesn't affect that number of liquidity provider shares, but adding or removing liquidity will cause the number of liquidity shares to fluctuate. It'll cause it to scale by the same amount that the quantities scale. So liquidity tokens will get minted or burned depending on whether alpha is greater than 1 or less than 1. And so then the question is, are depositors of assets into DeFi protocols safe from risks including exploitation of the system by arbitrageurs conducting economic attacks to drain those assets by using or abusing the operations offered by the system? And then in those kinds of scenarios, the features of DeFi that we that we like, such as its accessibility, composability, and disintermediation of humans, become not features but bugs if you've now disintermediated human risk managers and human regulators, then this may amplify the feasibility and or the impact of an attack. And then the question of which markets admit or do not admit arbitrage, which is already crucial in traditional finance, takes on additional significance in DeFi. So an early answer to this comes from a blog post by Vitalik, who says, a reserve bleeding attack on a market maker that preserves this kind of invariance property is impossible. Actually, he used the word path independence, which is in my framework, that's a specific type of invariance, but I'll take the liberty of replacing that word with invariance. Even if some trolls successfully create a market panic that drops prices to near zero, when the panic subsides and prices return to their original levels, the market maker's position will be unchanged, even if both the price and the market maker's balances made a bunch of crazy moves in the meantime. So to make this concrete, suppose there's a crash in the price of the blue coin as denominated in the red coin. The pool then loses the red coin but gains the blue coin that has been dumped into the pool by traders looking to get rid of the blue coin. Now that in itself is not an arbitrage according to the definition that I've proposed. That's to really see whether it's an arbitrage, we have to think about the round trip, to think about what happens when traders buy back the blue coin from the pool to make a round trip. Well, in that case, the quantity of red coin will return to its original level. So in that sense, it's not an arbitrage. And that's what Vitalik's saying. And then the question is now, what types of arbitrage can be ruled out? He says reserve bleeding, but can we be more general than that? Are involving what types of operations? Is it just swaps? Or what if the menu of operations also includes liquidity provision and liquidity withdrawal? Arbitrage resulting in loss of what type, in what sense? I've already given two possible interpretations of what it's meant by arbitrage. How general can we make that notion of arbitrage? And then what type of invariance is sufficient to rule out arbitrage? What kind of invariance is necessary to rule out arbitrage? Does this logic apply to protocols outside of this UniV2 type of decentralized exchange? And are these invariants unique? I'll save you the trouble of asking ChatGPT to summarize my paper by reading the answers in advance. Arb involving what operations? Any operations supported by the invariant function. Arb involving loss of what type? Any type expressed by a partial order D, which we'll call the dominance order. What type of invariance is sufficient to rule out that arbitrage? Well, existence of an invariant function that's increasing with respect to that dominance order is basically the generalization of Vitalik's thesis that an invariant makes it impossible to arbitrage a DeFi protocol. What type of invariance is necessary? Well, it turns out that the existence of an increasing invariant is both necessary and sufficient. And that's because its invariance essentially always exists. That's the title of the talk, all AMMs or CFMMs. And whether it's arbitrageable hinges on whether there exists an invariant that is increasing with respect to the dominance order that defines the notion of arbitrage that you're using. Does it apply to protocols outside of Uniswap version 2 type DEXs? Yes, it does. This applies to all DeFi systems, all DEXs, all lending protocols, all systems, all networks of any combination of these various primitives. And are invariants unique if and only if the market is complete in a sense that we'll define. So there are some related axiomatic approaches in other papers, but I would claim that what we're doing here is kind of orthogonal to what they're doing. The literature covers relatively many features of a relatively narrow set of systems. For one thing, these papers are all talking about DEXs, and they have further restrictions in each paper. Whether it's just a single pool, or whether it's a DEX in which all transactions are reversible, or or any of these other restrictions, but we're trying to be more general than that, but at the same time focusing on relatively few features rather than a whole menu of features that's elsewhere in the literature. And so we want a broad set of systems, but a relatively narrow set of features, namely this fundamental triad of arbitrage, invariance, and completeness. And we also want to be fully flexible on, as much as we can, on what's meant by arbitrage. Another point of contrast that these complementary approaches are largely geometric. Our approach is non-geometric. It doesn't assume anything about convexity, smoothness, differentiability. There's another strand of literature that tries to quantify the loss experienced by liquidity providers versus various benchmarks. Including work by Agostino and Siamak and co-authors. They try to quantify loss metrics, whether it's impermanent loss or loss versus rebalancing, in terms of features like the price dynamics and the geometry of the AMM. And so what we're considering here is more of it's not about quantifying things. It's really just a binary kind of existence or non-existence question, but with respect to general notions of arbitrage and with respect to general system designs. So in terms of geometry, I'm neither assuming geometric properties nor benefiting from the insights that can be gained from geometric properties. Okay, so the general framework is that we have some state space X. So X can be a space of all the bundles of coins that the AMM could hold. So an element of the state space could be 15, 240. Another one could be 60, 60. Right? So these are states in the system. In the general framework, it can be any state variables. They don't have to be balances. The state variables don't even have to be real numbers. We could be in non-Euclidean space. But all the examples, we're in Euclidean space in this presentation.
What's an example of a state variable that's not a balance? Is it sort of an abstract?
Right. So a state variable that's not a balance could be the liquidity variable in a Uniswap V3 bin, which is neither the amount of blue coin nor the amount of red coin in that bin. It could be a price. It could be the implied price as calculated by the ratio of the blue coin to the red coin. So this M function maps each state X to the set of states M of X obtainable from X by a single transaction. And transactions doesn't just include swaps, it can include liquidity operations, it can include borrows, it can include lends, it can include whatever liquidation transactions the platform supports. Any operation supported by that protocol can be included in this. Now, since all smart contracts consist of operations on state variables, these market systems include not only decentralized exchanges, but all of DeFi. So here are some examples: with fees, without fees, with liquidity operations, without liquidity operations. So let's now define M2 to be all the states that you can reach from X using 2 transactions. M3 to be the states that can reach from X by 3 transactions, and so on. M infinity is the set of states that can be reached from X by any finite number of transactions. And then let's define an ordering on the state space where we'll pronounce this as precedes or reaches or goes to. So we say that X precedes or goes to or reaches Y if and only if Y is in the set of states that can be reached from X by any sequence of 0 or more transactions. And then we'll define an equivalence relation on the state space by saying that state X and state Y are equivalent if and only if Y is reachable from X and X is reachable from Y. And define a strict partial order on the state space by saying that X strictly precedes Y if and only if X reaches Y, but Y does not reach X. So if the transaction from X to Y is supported, but the reverse transaction from Y back to X is not supported, is not a legal transaction according to the contract, then we say that X strictly precedes Y. Now, if there's a real valued function on the state space that has the property that whenever X reaches Y or X precedes Y, that the function evaluated at state X is less than or equal to the function evaluated at state Y. And moreover, if the reverse transaction is not supported by the system, that in that case the inequality is strict, then with those two properties we say that K is an invariant. So the invariant that we've seen already is this product function. This product function is such that if the product of the new state is such that if state X goes into the state Y, or that's a legal permissible transaction according to the system, then the product at the original state is less than or equal to the product in the new state. And this is valid even if the protocol charges this 30 basis point fee that it does in reality. So in practice, that constant product is not really a constant product. The product is increasing with each transaction because that constant product rule is applied not to the balances of the new coins, but rather to the balances of the new coins less that 30 basis point fee. So in fact, that constant product is not a constant, it's actually increasing with each transaction. Okay, but then, so we have that one ordering that describes the functionality of the system, but then there's another ordering which describes what we consider to be an arbitrage, and that second ordering we'll call a dominance order. That's a strict partial order on the state space. The first type of dominance that we've already seen you might call Pareto or product order, which is why it's written with a d pi, and state X dominates Y in that ordering if the quantities in state X of each coin are greater than or equal to the quantities of the coin in state Y for each coin, and that at least one of those coins is strictly bigger in the original state than in the state X than in the state Y. But then there's another kind of dominance order that we could define where instead of looking at the raw quantities, you look at the quantities normalized by the number of liquidity shares. And that we can call Pareto per LP share ordering. And that's a second example.
So in this, should Y be strictly preceded by X when we define this ordering? So Y is a state that can be reached from X?
No, that's the notion of arbitrage will link the two orderings, but the dominance order is not defined with respect to any particular system. It's the dominance order just reflects our notions of when is one state better than another. The ordering induced by the DeFi system reflects what transactions are permissible in the system. The dominance order reflects what states are better than other states in this unambiguous sense. Arbitrage links the two notions. We say that a market system admits arbitrage if there exists two states such that X reaches Y, but X dominates Y. Because if that's the case, then that system allows some sequence of transactions to transform it into a strictly worse state. And the point here is that the meaning of worse is entirely flexible. Any strict partial order on the state space can be taken to be the definition of what's worse. Okay, and then what do we mean when we say that an invariant function is increasing? Well, we mean increasing with respect to the dominance order. So this increasing property then is not to be confused with the invariant property. The invariant property, the fact that it's an invariant means that it's increasing with respect to this reachability order. And that's just a function of what transactions are permissible within the system. There's the second ordering called this dominance ordering, which is not about what transactions are permissible in the system. The dominance ordering is about what states are unambiguously worse than other states. And this increasing property is a compatibility of those two orderings, right? It's saying that the invariant, that the function has this monotonicity with respect to the dominance ordering. And if a market system has an invariant, we say it's a CFMM. If it has an increasing invariant, monotonic with respect to both the dominance ordering and this reachability ordering, then we can say that it's a DCFMM to specify the dominance ordering with respect to which it's monotonic. So I just want to quickly mention that there's another definition of CFMM in the literature, in which a transaction is allowed if and only if there's equality between the invariant function at the proposed starting state and the proposed ending state. So in other words, this would be the case where that product is not allowed to increase as you go from state X to state Y. That product is required to stay exactly the same. I would call that something different. I use a euro sign, but I pronounce this sequel FMM because equality is enforced in that case. And so this more restrictive notion of CFMM essentially rules out any concept of fees being collected by the pool and accruing to the pool, for instance. And so there is this other definition of CFMM. The definition that I'm favoring in this paper is in agreement with a paper by Ramsier, who argues that the constant function market maker name may suggest that you can transform from state Z to state X only if that function, imagine a product function, the product function in the new state is exactly equal to the product in the original state. But real-world CFMM deployments only check the weaker condition that the new state has a higher product than the original state. I'll also claim that the inequality definition of CFMM agrees with the common usage of CFMM, in which Uniswap v2 and Curve are described as CFMMs, which Wikipedia does. So this sentence from Wikipedia is not valid if CFMM is defined to enforce equality. If CFMM is defined to allow for this inequality, then the statement in Wikipedia is valid. Okay. So I want to define now an AMM to be a continuous market system. In order to do that, I have to define what's meant by continuity. In order to define continuity, we need to talk about topology. And so let's imagine that the state space is endowed with a second countable topology. That means it has a countable base, meaning it has a countable family of sets such that each open set is a union of members of that family. In the case of an uncountable state space, that's a subset of Euclidean space, you can let the topology be the ordinary Euclidean topology. In the case of countable state spaces, you can let the topology be the discrete topology. Both of those are second countable. And you define the market system to be lower continuous if the lower set at any state x, meaning the set of states that are strictly preceding x. In other words, the set of states that can go to x, but the reverse transaction is not allowed, is an open set. And define an automated market maker to be a lower or upper continuous market system. Upper continuous can be defined in an analogous way. And I claim this definition is natural. I claim that continuity always holds in a truly automated system because the concept of automation implies a machine, at least automation in the classical sense, implies a machine with a countable state space and therefore the existence of a second countable topology that automatically implies continuity, namely the discrete topology. And there are statements in the literature that present CFMMs as a subset of AMMs, right? Which is true, but more is true. All AMMs are CFMMs according to this definition of CFMM. The concept there is that if you have a countable state space, then you can assign an invariant function by just letting, by putting a weight on each of those countably many points, put a weight of 1 over 2 to the n, and then define the function at any point to be just the sum of the weights of all the states that precede that state, that are transformable into that state. So if this is where your state is, then you, and all the other states that precede this state all have weights on them, sum up the weights of all the states that strictly precede this state, the states that all transform into X, but the reverse transformation is not allowed by the system. Sum up those weights, and there's your invariant function at X. Now, this is, okay, there's some issues with this intuition, right? First of all, it's being drawn as if it's some kind of linear order, when in fact it's a partial order. The other issue is that you don't necessarily have only countably many points. There could be uncountably many points, but that's the point of the topological assumption. You can instead of summing up over points, you can sum up over elements of that countable basis that precede X, and that's the idea. And so this goes back 60 years to work initiated by De Breu, but then extended in the subsequent decades in utility theory. Okay, so then the first fundamental theorem would be that if you have a CFMM that is a DeFi system that has an invariant function, then it's arbitrage free. And so this is basically Vitalik's argument, but just generalized to arbitrary orderings that define what does reserve bleeding mean, right? So he has one notion of reserve bleeding, but his intuition is perfectly applicable to other notions, the general notions of reserve bleeding as encoded by this notion of D, this dominance ordering. If a market system accepts gifts, then we'll say it's giftable. Intuition being that, well, the definition being that the market system allows you to make transformations that from a dominated state into a dominating state. So if the system's asset wallets accept donations, then in that sense, it's giftable on an intuitive level. Or if the state space doesn't contain any pairs where one state dominates the other, then in a vacuous sense, it's giftable. So we'll call a DeFi system to be a giftable market system that's also continuous. And I claim this definition makes sense given DeFi's home on the blockchain. It's very easy to make deposits into a wallet that's not yours, right? It's hard to spend out of a wallet that's not yours. It's very easy to send garbage coins into wallets that don't belong to you. So in that sense, it's natural to have a giftability assumption on a DeFi system. If that's the case, then the converse is also true. That if M is an arbitrage-free giftable system, then it must be a CFMM. It must have an invariant. That invariant must be increasing, and that can be verified. So to combine those necessary and sufficient conditions, a DeFi system is arbitrage-free if and only if it has an increasing invariant. So returning to the initial questions, what kind of invariance is sufficient? The existence of an invariant function that is increasing, and that's not only sufficient, but it's also necessary. Okay, so here are some applications, which I'll just maybe skip most of these. If you have a system of constant product x's on the same assets, then arbitrage exists in the sense that we've discussed, in that summation sense. If you've Uniswap V2 a single pool with allowing liquidity operations, allowing fees, allowing admin fees that actually haven't been turned on yet, but which Uniswap has reserved the right to turn on, even with all of those fees. So this is above and beyond this is separate from the 30 basis point fee. It's the ability to collect part of the 30 basis points by minting liquidity shares and thereby diluting the liquidity providers, and that would be a fee collected by Uniswap. That hasn't been turned on, but governance is in the process of turning that on or proceeding toward that direction. Even if that's turned on, there's still no arbitrage. We can analyze Uniswap v3 with general liquidity profiles, and if we define a notion of what it means to arbitrage a Uniswap v3 system of pools, then we can also conclude that there's no arbitrage in that sense. If you have a non-homogeneous AMM, and you define the liquidity operations in a naive way, that's arbitrageable. But if you define it in a more reasonable way, that's maybe not as simple, but more logical, then there's no arbitrage. And then in the case of a simple lending protocol, there is arbitrage. Maybe I'll say a little about the lending protocol just to emphasize that what I'm presenting here is not just limited to the DEX case.
Non-homogeneous means the invariant function is non-homogeneous?
Non-homogeneous meaning that there exists no invariant function that's homogeneous. So this would be the case of a DEX in which you're allowed to transform from asset balances X1 blue coin, X2 red coin into blue and red balances, as long as the sum of the blue coin balance and the square root of the red coin balance is greater than what you started with. So if you, in this case, this is an example of a non-homogeneous DEX. And in this case, if you maintain this same rule even after doing liquidity operations, then this will admit arbitrage. So the swap rule has to be modified to essentially do a perspective transform in order to modify the swap rule in the case of this non-homogeneous AMM.
So just, so that maybe leads to my question. Some of the earlier papers you cited argue that invariance always exists homogeneous ones through a perspective transformation, but I guess they're assuming some kind of convexity.
So, right, I mean, I've seen this claim made, and it's not in the same sense that I'm presenting. I mean, here's an explicit example of a DEX that does not admit a homogeneous invariant. Assuming that such an invariant exists would result in a contradiction. So there is...
The core thing that's going on here is like the reachable set is non-convex, something like that? Or those earlier results are just wrong?
I think there's an incompatibility in the definition of what they mean by homogeneous and what I mean by homogeneous. I think that's the root of the issue there. But this invariant, this transition rule very explicitly does not admit a homogeneous invariant function. And you can easily verify that directly and numerically. And in such designs, one cannot simply reuse this rule after a liquidity operation has been made. Otherwise arbitrage would get introduced. There has to be this perspective transform applied to the swap rule in order to update it properly in the presence of liquidity operations. And then maybe one more example that's kind of different to emphasize the flexibility here. Suppose that the system consists of both a DEX on the blue asset and the red asset, so it's a pool of the blue coin and red coin, as well as a lender. And so the lender accepts a deposit of D2 red coins from the lending protocol accepts a deposit of D2 red coins from some lending participant, and it lends out B2 quantity of red coins, where B2 can't be bigger than D2, but it also has to be subject to the borrower depositing some D1 blue coins as collateral. And okay, you might try to put restrictions on how much can get lent out, right? You might restrict the amount of borrowing to be less than or equal to the value of the collateral. So this is the amount of blue collateral that's been deposited, and you're multiplying it by a factor that converts from blue coins into its liquidation value, basically. This is the number of blue coins, but you want to convert it into red coins. And to convert to red coins, you multiply by the price, x2 divided by x1. But you can also furthermore add a term to the denominator that accounts for the market impact. The fact is that x2 divided by x1 is like the instantaneous price. But if you're trying to liquidate a block of size D1, then you won't get the price x2 over x1. You'll get a worse you'll get a worse price, and the amount, how much worse, is due to the x1, the extra term of d1 in the denominator. So this is a liquidity adjusted collateral value, and then R is like 75%, right? It's trying to give some kind of cushion to say, okay, you can't borrow against the full amount of your collateral. You can only borrow against 75% of the value of your collateral. Okay, but even with those guardrails in place, the question is, well, does it admit arbitrage in the following sense? Let's define the dominance order to mean that a solvent system dominates an insolvent system, meaning that an original state dominates the primed state if the original state is solvent, meaning that the value of collateral is bigger than or equal to the amount of red coin that was borrowed. However, after the sequence of transactions, in the primed state, the amount that's borrowed is greater than the amount of collateral converted into red coin by that exchange rate, that effective exchange rate, accounting for the market impact. So this type of ordering is just that a solvent system dominates an insolvent system. Well, under those definitions, there's an Oracle manipulation attack. Now I'm going to write it without I'm going to drop one of the state variables because okay, the 20 coins that were lent doesn't really play a role now. As long as I don't borrow more than 20, I'm fine. Okay, so and that should be a red 20. That shouldn't be a blue 20. So what kind of arbitrage is possible? Well, if the red and blue coin's true value or fair value is parity, meaning, okay, originally there are 10 blue coins and 10 red coins in the DEX, which is consistent with the idea that they're at a 1-for-1 value ratio, and the second two coordinates are the lending portion of the lending module of the combined system. Well, here's what the attacker does. The attacker dumps 40 red coins into the DEX, driving up the value of coin 1. Coin 1 was worth one red coin here. Coin 1 is now worth 25 red coins here. So the attacker has artificially inflated the value of coin 1. Now, that inflates the value of collateral. So with 1 unit of coin 1 now, the attacker can borrow 12.5 units of the red coin. I put borrow in quotation marks because the attacker has no intention of paying back the 12.5 units of red coin that they borrowed. The attacker is perfectly happy to lose the 1 blue coin that they've deposited as collateral and keep the 12.5 units of the red coin. The attacker will now buy back the 40 units of red coin that he had dumped into the DEX. The price goes back to parity, but then the attacker walks away with 12.5 red coins after having deposited only 1 blue coin as collateral. The DeFi bank is now insolvent. It has bad debt of 12.5 red coins against only 1 blue coin as collateral. So this is an example of this, of another notion of arbitrage that kind of captures this idea of an Oracle manipulation attack. Well, it's a toy example, but it's reflective of a real world example, such as when depositors at Mango Markets lost more than $100 million to this type of attack in October 2 years ago. I mean, the attacker ended up returning, I think, more than $60 million of the funds, so the majority of the funds, but in a bid to keep himself out of prison. And claimed that all of our actions were legal open market actions using the protocol as designed, even if the development team did not fully anticipate all the consequences of setting the parameters the way that they are. The SEC did not agree with this, and so he's been convicted of commodities fraud and wire fraud, and he's in federal prison awaiting sentencing. The same prison as SBF is currently in, as far as I understand. But the broader point here is that the development team, it's true, did not fully anticipate the consequences of their market design. And I think the broader point is that a development team should anticipate those kinds of economic attacks. Okay, there's a second fundamental theorem that I don't have time to discuss, but it's basically saying that a CFMM has a unique invariant if and only if it's complete, where completeness means that for any two states x and y, either x reaches y or y reaches x. At least one of those transactions has to be supported by the protocol. So in conclusion, all AMMs are CFMMs and therefore have invariance by definition. First theorem is that a DeFi system is arbitrage-free if and only if it has an increasing variant. And second theorem is that it has a unique invariant if and only if it's complete, as defined in the previous slide. So the increasing invariant in nonlinear AMM theory, therefore, has the same role, analogous role at least, as the martingale measure in linear markets. And then these two results then become analogous to the first and second fundamental theorems of asset pricing. Last slide, implications for market design. If your system has to defend against a D exploit, then make sure it has a D increasing invariant. This is not just sufficient, it's also necessary. All DeFi protocols and systems have invariants, not just DEXs. Non-DEX DeFi designs rarely reference invariants, but they should. So the recommendation to the designer or documenter or auditor of a non-DEX system is to re-examine in terms of invariance, extend the state space to be not just asset balances, but also quantities like LP tokens, loans, collateral, prices, and so on, and extend the notion of arbitrage or exploit to not just protect balances, but balances per liquidity provider share, and to protect solvency of lenders. And another viewpoint on this is that this is saying to do formal verification, which is something that's done in hardware and software design, but you know, it should also be done in economic and on the economic and finance level as well. I'll stop there.
We have like 3 and 7, and one quick question. Yeah, Brian.
So I think for the reserve bleeding example, Vitalik was sort of saying that the price will return back to the original level after the Oracle manipulation. But if you have external prices of coins that do not return to their original level, then the price in the AMM is stale. How does like this framework rule out like the arbitrage from stale prices?
So why is it bad to have a stale price? It's bad to have a stale price because it can be arbed against prices elsewhere that are not stale. So that kind of situation can be, can be modeled using a similar type of framework as this.
Like if I define the partial order to be like the price weighted value of assets and pools, so it's just like one number, not a tuple. So
okay, so the price, I mean, weighted by what price, right? So if you weight it by the price implied within the DEX, then it's always going to be double the value of your numeraire coin because it's 50-50. It ends up being 50-50, and so if it's internal, then it's always going to be 2 times x2, 2 times the value of the red coin. If you define price with reference to an external price feed, then yeah, it's very much arbitrageable in a similar sense that we've seen here.